Perfect. Hello, everyone. Good morning, good afternoon, or good evening. And thank you so much for joining us today. My name is Caroline Maître, and I will be your webinar host coming to you live from Bordeaux, France. So today's webinar topic, we will be looking at system simulation for aircraft design. I am delighted to welcome other speakers today. So Mr. Florian Schüssler, CEO from ACAM Engineering, and Mr. David Morand, Aerospace Business Development Manager, SimCenter System Simulation from Siemens Digital Industries Software. I will give a very short bio of the speakers and we will be ready to start. So Florian has many years of experience as a simulation engineer, In the course of his career, he has taken on the technical management of more than 150 engineering projects in the field of CAE. And in addition to his work as managing director from ACAM Engineering, he is a lecturer at the Vienna University of Applied Sciences for finite elements and computational fluid dynamics, and he works as a court-certified expert for finite elements. David has held several business development positions related to system simulation in Asia and Europe, with a mechanical engineering background and MBA from Lyon University. He is now part of the SimCenter Aerospace team to develop system simulation solutions worldwide. Perfect. Thank you so much, gentlemen, for being with us today. We are really grateful. David, you are the first one to present, so the floor is yours. You can now start.
So thank you, Caroline, and hello to everyone. So it's a pleasure to present you today the use of system simulation for aircraft design. I will go during this 40-45 minutes presentation with Florian through the following agenda. We will look rapidly about the aircraft systems challenge from the aerospace industry, how systems performance engineering with SimCenter address this challenge. We will look at typical application available with our solutions, and especially we will make a focus, thanks to Florian, on the simulation of fuel system management in relation to severe flight dynamics condition. I think it's a subject very interesting, and we will conclude these presentations. You can let us some question and answer in the Q&A window. We will reply at the end of the presentation your questions. So going for industry challenge, like any other industry in the world, sustainability is a key word, and there is a need for any aircraft maker or supplier to actually reduce its CO2 emission consumptions to address a better world. We have recently seen that last year a resolution was passed by EIT member to actually have a net zero carbon emission from their operation by 2050. So it's become really mandatory to address the issues, the ecological issues when developing new aircraft. And among these solutions and possibilities, pick one, which is also a trendy one. It's actually especially for the small aircraft and for what maybe come in the future via electric air taxi. It's actually the electrification of our propulsions. So there is a new trend and completely change in how aircraft can be, propulsion can be evaluated, can be designed. We have also recently seen R&D and project around H2 propulsion, and this leads actually to a complete rethinking of how our concept of aircraft can be developed. On the same time, configuration of aircraft has to be rethink, where various types of wing body can be evaluated, and leading to looking at a new distribution of masses, flow elements into the aircraft. So So with this, trends actually affect design from conceptual design, preliminary design, and detailed design all along the process. Engineers have to deal with more complex product. Still, they have to reduce time to market and reduce risk, a safety issue being very important, while actually working more and more in a seamless process and connecting actually the removing barrier between silos and teams and disciplines. And so simulation and engineering work can actually be a part of this challenge in order to enable a rapid design to prototype work. If we look a design process, actually where simulation can be used and what it means to use simulation all along design process, from requirement down to launch of product. Actually, it means to work with requirement, to be able to co-simulate various tools, to be able to connect also the physical world with the electronic and control world, with simulation in the loop or hardware in the loop, to be able to use complex model embedded in, let's say, a virtual representation of an aircraft at verification and validation in order to use simulation at every step of the process. I would like to see now how SimCenter system simulation address this challenge and how it can be used in such a process. A short recall about system simulation. System simulation is actually a composition of two words, the control modeling and the plant modeling, where we simulate on steady state and dynamic point a complete system, smart systems, in order to predict its performance. And system simulation can be used at various steps of a design cycle, where it can be a first level, sufficient enough modeling level to address the first high level design requirement. It can be also used between high detail level and detailed design models, where usually we use lots of 3D CFD. And the system simulation can be either on the left side of the design cycle boundary condition for such a model, or they can be also a container to on the component testing and subsystem testing. They can embed a result from CFD software or finite element software detailed design inside the model in order to simulate more rapidly actually a complete system at verification and validation phases. So when we use system simulation all along this design, we use our tools, of course, but we also use a kind of methodologies. Aerospace industry is one of the leaders of MBSE methodology. So we try with system simulation within SimCenter to have a virtual system integration point of view when we develop a model with a componentization of the element, where each element can be packed in component and that can be reused in order to follow a breakdown structure of a complete aircraft and simulate actually the combination of various systems together in order to, at pre-design stage, evaluate the behavior, but also at verification stage, evaluate safety procedure, and so on. I'll switch here. How does it really apply on the supply chain? Actually, is that system simulation can be used by some component maker. For example, if we took the example of valve and pumps builder, they can use such a kind of models that reproduce the dynamic behavior of a given pump, for example, that can be integrated virtually in a braking or steering system of a tier 2 supplier, that can be itself integrated in a more complex system of a landing gear that at the end will be integrating into a virtual model of an aircraft, being able to simulate not only steady state but transient behavior and dangerous maneuver, for example, of an aircraft. So system simulation, as we are used to in CAD or CAE model, can also be a link and can enable users on various supplier and customer to exchange model between each other. Let's look at typical application and where system simulation is used in the aerospace industry today. The way we organize our tools and solution is either by application, but we also like fuel system, electrical system, controls or propulsion systems. On the other hand, we have the capability actually to group this application or technology element, which are based mostly on libraries of component, pre-made component. We can also group them in order to address ATA classification and to create a virtual aircraft model based on this ATA, following more a systemic approach of creating the models. Short zoom in on engine aircraft engine, where we have also the capability to simulate from primary flow and combustion and secondary airflow down to nacelle system and accessory gearbox, a full engine models. But we also can work on, and we have several customers working on actually electrification and hybridization of the propulsion. So be showing the capability to address new technology and new technology and increase innovation in their design process. So as a series of examples, an application example where system simulation can be used, we will browse through these 5 examples. What can be a use of fuel systems, move toward electrification, look at how to balance, to have a easy balance of different attributes for an environmental control systems design, front loading of a full hydraulic systems, and finally look at integrated thermal and power management. So in our 1D system simulation, actually, we have capability to represent the various component piping system, reservoir systems and pump system of a fuel management systems, and take into account the connection of this subsystem to actually also the flight dynamics. I will not go really into detail on this, because you will see in a few minutes that Florian is addressing this subject with very nice examples. We can also use system simulation to be innovative and to validate at early design stages various kind of new propulsion types. So an example here would be the integration of an electric powered mid-range aircraft, or the creation of a thermal management model of the batteries in order to assess not only power demand from the electric, but also thermal behavior of the electric circuits and electric power machine at steady state, but also transient behavior during a complete flight of the aircraft. Looking at comfort of passengers, it is sometimes very important, and here we have a nice example of coupling, as just presented you before, or coupling between 1D system simulation and 3D, where the behavior of passenger and the cabin airflow can be represented with 3D software. So for this example, it's Star CCM Plus models that is connected to or 1D system simulation software HAMSIM that is modeling the complete ECS systems. Such kind of model will be able to, at the same time, balance between power demand for the ECS and also comfort demand from the passenger in a single co-simulated model. We have talked before on the capability to link various components and simulate a complete aircraft behavior in a hard condition. This is an example of interest where here we simulate a rigidity takeoff of the aircraft, meaning that one of the engine at takeoff is having a problem and we need to stop rapidly the engine. So the hydraulic system is under high solicitation, and in this model we will represent all of the hydraulic, flight dynamic system, landing gear, strut reaction, taking into account of high fidelity models and strong coupling between dynamics and hydraulic behavior. Finally, as we have seen various applications, the goal of system simulation is not to work sometimes on one application at a time, but to couple them together and to be able to represent the different system itself under a complete aircraft flight mission and simulate either only in system simulation, but by coupling with other tools, the different reaction of the systems to address various attributes. To illustrate one of the applications of interest and the coupling between fuel management and flight dynamics, we will showcase you a presentation by Florian, actually, that will make you discover the way we simulate an aircraft which is under severe maneuver.
Thank you very much. Also a warm welcome from my side. My name is Florian Schüssler. I'm the Executive Officer of ACAM Engineering. We are a company with focus on simulation engineering based south of Vienna, and together with our customer and partner Diamond Aircraft, we worked on this specific topic, aircraft fuel system simulation, and especially for extreme flight conditions. And all the insights we have gained and how we worked on this project, I want to show and share today with you. A quick look into today's agenda. Quick introduction to ACAM Engineering and Diamond Aircraft. A quick overview, AMESIM and the fuel system library we use in there. Then how we built the fuel system, what were the challenges. And then the three project topics, refueling, optimization, then the spinning simulation, and an issue with full probes in stable inverted flight. Okay, Diamond Aircraft is one of the leading manufacturers of small composite aircrafts. They have a very large amount of composites within their airplanes, and they are in the field of general aviation, flight training. For example, the big airlines like Lufthansa use the Diamond twin-engine aircrafts for the pilot training. Then they also have a special mission aircraft division. And last but not least, they have developed a turboprop trainer, which is named DART. And with this 650 horsepower turboprop airplane, it is possible to train the maneuvers instead on fighter jets, for example, because the hours where the airplane is in use, they are quite cheaper than if you do all the maneuver training really on the fighter jets. And within this turboprop trainer development, our fuel system optimization project is embedded. And Diamond Aircraft itself is also based in Austria. It's quite near from our office location, also south of Vienna. And they also have manufacturing facilities in Canada and in the People's Republic of China. All right, here is a short overview of the Diamond Aircraft product range, starting with the small aero clubs on the left, then different types for flight training, airplanes for private pilots, single engine or twin engines. The biggest one for with 5 seats is the DA62. And the same airframe, a little bit adopted to one engine, is the DA50, which is also quite new and certified, I think, last year. And for special mission, there are also twin engine airplanes adopted with camera holes, different special mission equipment, mostly specified and unique to the customer wishes. And the last airplane on this list is the Diamond Dart, and this is the airplane we worked on in this project and did the fuel system optimization. Also just a slide where you can see the locations. So Diamond is also very international in their focus. So they have manufacturing sites in Canada, in Ontario, and also in Xinjiang, China. Their headquarters is in Wiener Neustadt in Lower Austria, and they also have a division called Austro Engine, and for the small airplanes they are producing the engines itself and have also quite a large amount of development within that field. Then the last slide of introduction, Acam Engineering. This is my company. We founded the company in 2015. We moved to a new and own engineering location in Lower Austria last year in April, in the mid of the pandemic, which was quite challenging. But now we are very happy, and to this day we have successfully finished more than 150 CAE projects, mainly with Siemens SimCenter products, or nearly all were done with SimCenter Siemens. And with Diamond Aircraft together we have quite a strong partnership. The one term of this partnership is the support and delivery of the Siemens industry software, and the other part of this partnership is the support with services. And here are some examples of what we do there together. We have done the fuel system simulation. We do a lot of stress analysis of composite structures and flight control systems, for example, one colleague of me is doing right now. We support the Austro Engine company in the development of their engines, mostly with multi-body domain simulation combined with structural analysis. And what we really like is it's a very embedded work, so we have a good knowledge and know-how transfer in both directions, and we are very happy with this partnership. The next 2 points are the overview of the fuel system library and the creation of the fuel system. Okay, as you surely know, AMESIM is based on libraries with different preset blocks, And one of them is the aircraft fuel system library. There are ready-to-use components in there which you can drag and drop in your model and create whole systems out of it. And with that, it's possible to simulate any functions of aircraft fuel systems, and also to integrate the fuel system with the relevant subsystems interacting with it. Example given: mechanical, fluid, pneumatic, whatever. It depends on the blocks which you are linking other components to, but it's open to different domains within AMESIM. And on the right, you can see a screenshot of the available blocks in the fuel system library. There are tanks available with simple or complex shapes. We will discuss it later on, how to model it. Then there are pipes, there are free fuel surfaces, and also fuel probes. There are blocks for the measurement data you have already gained to run your simulation with measurement data. So it's really a very broad range, but it's also easy to use because it's a drag and drop system, and based on your design plan, you can build your 1D model also very easy. Also, fluids and materials are at airplane fuels not quite easy, because it's not water or air flowing through the system. It's, for example, Jet A1. So you need the fluid and material data, and this is also included in the aircraft fuel system library. So you have predefined materials in there. Example given, Jet A1, which we used also. One step of building the 1D fuel system is to import your CAD geometry to create the tank shape files. So if you look to a fuel tank, it's not an easy geometry. Mostly it's quite complex because there are freeform surfaces, maybe there are holes in there, and so on. And for that, you need a tool first to create the tank shapes, and afterwards to visualize your geometry and the fuel within that tank shapes. And the process is to import your CAD geometry as a step or different exchange formats, and then switch into the fuel system plugin. And in this plugin, you are using the single tanks, creating the tank shapes out of it, which are text files, and then link it in AMESIM to your component. And this is the basis for the analysis of the 1D system. And the last step is to visualize your fluids inside the tank, the distribution of the fluids, and how it's moving related to some airplane movement. And this is done with the visualization assistant, which makes the fluids within the defined geometry visible. Given information, we can now switch to the modeling of the complex tank geometry, first in the refueling optimization, and how we have done that on this next slides. The constraints for that, the airplane itself features a turboprop engine, aerobatic capability, and it has a wet wing, which means the fuel is completely filled inside the wing. How is the process to create these tank shapes? First, you need the cut geometry, which is quite easy because it was provided from the design department. Then you switch into the cut editor, create the tank shape files and the visualization. And the tank shape files, it's kind of a cut of cutting planes through the single tanks. And the parameters of this cut, are written into a text file. And this text file, which is called the tank shape file, is used for the analysis of the system. And within that dialog, you also create visualization files, which then helps you to visualize the results of the simulation. On this slide, you see an example how these files look like. So on the left, you see what is created. We have a log file of the creation process. We have the step file for the visualization, and we have the info and the shape file. And if you look into the text columns, you see, for example, for the shape file, you see the center of gravity and different other information which is needed for the simulation, for the AMESIM simulation. And on the right side of the slide, you see how an info file looks like, and this is some additional information which is used to create the tank block inside of AMESIM. How this process looks like, you see in this small video. This is the center tank, which is necessary for the acrobatic flight maneuvers to continuously support the engine with fuel flow. You see on the left some tank sections, some ribs, so it's necessary to define the part of the tank. We subcreated it into different parts, and this is the assembly in AMESIM. As you can see here, this is the center tank, the modeling of the center tank, where you can see the different sections. So we have section 6, for example, upper and lower, and they are connected to other sections with the ribs. And the rib itself has also a shape file, so the holes in there to allow the fluid flow, they are also designed with those shape files. And so it depends on how many other aligning compartments you have or sections you have. So at least you have one rib to another tank, but it could be up to 6 depending on where your section in that case is located. So this is quite a complex modeling for that, but it proved very, very sufficient, and we really created very good and interesting results with that process. And having created all these ribs, shapes, and visualization files, you can, if you click on, for example, the center tank, you see on the right hand side, these files are linked within the fuel system block. On the lower, you saw the file for visualization. It's also here. Then you have to define a reference point just to align it and to set the orientation, which is also necessary for the visualization. And if you look to the upper part of the model, you see here these are the flight dynamics. So we have the acceleration data out of the spinning maneuver, which was recorded. And this is applied to this simulation with these blocks we see here on top of the system itself. So one part is the geometry, which is derived to the 1D model, and the other part is the flight dynamics and the conditions, and those together set the analysis of the fuel system. This 1D model gave us the opportunity to start with the refueling optimization, which you can see here. So bigger holes in the ribs reduce the fueling and refueling time, but bigger holes are not so good for spinning maneuvers, for example, because then the fluid flow is moving faster to other compartments, which is not the best solution. So the initial simulation was the refueling, as you can see here. The refueling port is at the end of the wing, and you see the fueling time, the fueling rate. You see in the center here with this point. This is the fuel probe. So you see when is some movement on the fuel instrument in the cockpit, and for that it was possible to do batch runs to look into a variation of different vent tube diameters, for example, increasing, decreasing the holes to reduce or increase the refueling time. Depends on what the aim of your simulation is. Insights, we switched to the spinning simulation. You mostly know, I guess, the spinning maneuver itself. So it's an aerobatic maneuver. It's a rotation about the vertical axis, and it creates a loss of altitude. And for the spinning simulation, we did the complete fuel system, the wing and the center tank, all together in one model. And the results which were from interest are the maximum hydrostatic pressure, which is relevant also for structural assessment. Then it was interesting to see the center of gravity of the fuel and the inertia tensor of the fuel. So these were the main results we provided. Yeah, and we applied the measurement data of the spinning, which you can see in this video, and it's at the same time step, so it's oriented in time to the visualization of the movement of the fuel system you can see here. And if we look into this video, we see how the analysis results compare to the real flight which is quite impressive. And if you play that in slow motion, for example, you can really get a very deep insight of your behavior in your tanks and in your wing, which is with the look to center of gravity also influencing the behavior of the airplane movement. Last topics in that presentation is the stable inverted flight and how this is affecting the fuel probe and the display in the cockpit. Fuel probes and stable inverted flight was the task for this simulation. In special, the simulation of different pitch angles with different fuel amount. In some, we ran 11 pitch angles with 5 different fuel amounts, resulting in 55 simulation runs. And the results, as you can see below, some screenshots out of that, where the fuel probe values and the center of gravity. And the fuel probe values, because they experienced some issues with the fuel display in the cockpit. And so we got some detailed insights of the fluid behavior in correlation with the fuel probe. And here you can see the stable inverted flight. And we have a fuel amount of initially of 40 gallons. Directly after refueling, 0 degrees roll, the first 2 pictures on the left. In the center you see the start of the inverted flight after 604 seconds, 180 degrees roll. And at the end you see the inverted flight, steady state, after 8,000 seconds in a 180 degrees roll. And if you look, these were quite interesting results with red. We see the display of the fuel probe, and it's kind of a pipe which transfers the filament of the pipe to the instruments in the cockpit to show how much fuel or how full the tank is. And here we got quite interesting results also in topic of the fuel probe itself. And you gain a lot of understanding to the center of gravity of the fuel and how the distribution of fuel in compartments is over time. So with that slide, I want to say thank you very much for your interest in our project, and if you have some specific questions, I'm very happy to answer. Thank you very much.
So in order to finish this presentation and go to the conclusion, we tried to present you in this 45 minutes webinar the way that system simulation can be used for aircraft design at various steps of the design process. And system simulation, we believe, enables to model complexity and take into account the various interaction between the various system and subsystem that are composing a product and an aircraft. It enables, as you have seen, and I think it has been well presented by Florian, to explore many possibilities and do lots of simulation by front-loading virtual tests. It also enables to have a kind of digital twin to assess the design challenge of any type of aircraft, especially when they are new technology-based aircraft. And as we've seen it, system simulation can be used by various actors. It can be suppliers, it can be OEMs, and the way it can be used can also remove silos between departments and various stakeholders. So we try to have this presentation for you. I hope this was interesting. Right now, we are happy to take up your questions and your comments.
All right, perfect. So with that, I would like to thank again our speakers and experts, so Mr. Florian Schüssler and Mr. David Morand. Thank you so much, both of you. Thank you for your expertise. And thank you all for joining and for your interest in Siemens Global webinars. So I will now close this session. Have a great day or evening. Thank you so much.